Hello. So in this final part of the chapter in year one or year 12 trigonometry, in this chapter, we're going to look at sort of mixing identities, trig identities with trig equations. So how can we use trig identities to get an equation we can solve, right? We actually kind of looked at this already. So it's not really anything new we're going to be looking in this particular video. But it's really good to kind of like recap and bring everything together, right? And so then that goes without saying then, we are going to need to recall our trig identities. So sine squared theta and cos squared theta is always 1 for any angle theta, right? Also tan theta is sine theta over cos theta. And you do need to remember both of them. But hopefully you got a lot of practice in. You've seen them quite a few times, so they're kind of like seeped into your memory now. But you do not get given that in the formula book, okay? But you're going to be using these with trig equations, right? Which again, hopefully, you should have a sort of good idea how to solve. At this point, we looked at many different types of equations in the last two videos. If you need to go back up to recap, have a refresh, you can go back and watch them, or however else. But that's what we'll be doing. Now, the other sort of thing I really want to emphasise then, go over explicitly before we go through the examples. Cast back to when we looked at quadratics. So say, for example, we had 2x squared minus x minus 1 equal to 0. Obviously a quadratic equation. You should know how to solve that. We can use it via the formula. You can factorise, you can complete the square. But completing the formula probably the most likely works every time, right? So I could just therefore say that the root of this, the two roots, would be minus b, which would be the coefficient there. So minus of minus 1 be plus 1. Plus or minus the square root of b squared, so that'd be minus 1 all squared, minus 4 lots of 2 lots of minus 1 over 2 lots of 2. And therefore, if I put that in the calculator, I get that the solutions are 1 or minus a half. Okay. Now, even from GCSE, hopefully you're very solid on that. That obviously, we just used the quadratic formula there. You can solve it however you want to, though. But why am I bringing this up? Well, actually, it turns out we can get quadratics with the trig functions as well. Because obviously, for this identity, for example, obviously we have sine squared and cos squared. So if you have a squared term, we're going to get a squared, right, in some sort of quadratic part. So for example then, say if I had then the equation 2 sine squared theta minus sine theta minus 1 equal to 0. Now hopefully you remember this, hopefully you can see this very, very strongly resembles the quadratic. Actually, it resembles the one we just did, right? Except, hopefully you see, instead of x now, we have sine theta, right? So if we then use the substitution, x is sine theta, and then we substituted that in, this equation would go to sine squared theta, that'd be x squared then, right? So that'd be 2x squared minus sine theta would be minus x. And then minus 1 equals 0. Well, that's the exact equation we solved. We can then solve this quadratic, which we already did, to then say x is 1 or x is minus a half. But we want to solve for theta, right? We want to solve for the sine of theta. So we need to then reintroduce our substitution, right? So then we would say, well, instead of x, it would then just be sine theta equals 1 or sine theta is minus a half. And so then actually, these two are trig equations which I can solve, which I know how to solve from the previous sections. I can then solve them two separate equations to get theta, okay? And that's literally the whole idea, right? The whole idea of this section is that you can convert a quadratic trig for a quadratic trig into and then we can solve it, right? And we call this, remember, a disguised quadratic, meaning it is a quadratic, but obviously it's different terms, right? But it is a quadratic equation, right? And we also did look at disguised quadratics in the first part of the quadratics chapter. So this is another type of disguised quadratics you need to be able to recognise and solve, okay? So you need to be able to recognise that this is a quadratic equation, which we can say that x is sine theta to get an actual quadratic, okay? But that's what we'll be doing, okay? We'll be basically, most of the questions will be basically boiling down to a quadratic, which we then can solve, okay? So hopefully you got the idea what we did there, okay? Let's move on to some examples then. So, we need to solve for theta in the interval 0 to 360 for the equations. So firstly, 2 cos squared theta minus cos theta minus 1 equals 0. Well, there we are. Hopefully you recognise this is a quadratic. It's a disguised one because it's not explicitly x squared plus x plus 1 or whatever. We have coses instead. But if we then said, if we use the substitution, so it said some u, right, is cos theta, then we can rewrite this equation, right? Because if u is cos theta, then we could say that u squared is cos squared theta, if we just square both sides. Therefore then, 2 cos squared would be 2u squared, right? And then minus cos theta would be minus u. And then minus 1 equals 0. And now that is a quadratic I know how to solve very comfortably, right? I can use whatever I want. Let's just use the formula, right? Actually, I think it's the same quadratic we did at the start, but let's just solve it again. So then u would be 1 plus or minus the square root of minus 1 squared minus 4 lots of 2 lots of minus 1 over 2 lots of 2. And that would be, if we put that in the calculator, 1. So u would be 1, or u would be minus a half. But again, we don't want to solve for u. Remember, we want to solve for cos theta or theta, right? So we need to bring back in our substitution. So if u is cos theta, then we can say that either cos theta then would equal 1, or cos theta would be minus a half. And so we can go on with proceeding to solve both of these equations separately, okay? So firstly, we have cos theta equals 1, and then we'd also have cos theta is minus a half. So let's solve this one firstly. So cos theta is 1, and also remember our interval is 0 to 360. Okay. There we are. So let's go on to solve this one then, firstly. Again, we can do inverse cos firstly to get the first solution. If we do that, inverse cos of that, we get 0, which therefore means the first solution would be theta is 0. So then to find the other solutions, we can consider the cos graph, right? Let's do it here. Actually, let's do it down here, right? So the cos graph, say between 360 degrees, it looks like that. Well, theta is 0 there, right? So that's when it's 1. So then the other solution would be actually at 360 then, right? So 360 would be the other solution there. And actually, that's it then, right? Between 0 and 360. Oh, actually, let me double check. Oh no, it's equal to. Okay, less than or equal to. Okay, there we are. So always pay attention to the question. So it could be 0 or 360 as well, okay? So these two solutions we can have. Those are the only two solutions then between 0 and 360. So actually there we are, okay? Cool. Then we need to solve this one. So again, let's do inverse cos again. First of all, we would get the answer of 120 degrees. Cool. So then to find the other solution then, so then theta, sorry, would be 120. To find the next solution, let's consider the cos graph. So 360 would be there. So 120, well, if 90 is there, the 120 would be about there, right? So then the next solution along would be there, beta. To find that next solution then, well, again, in the middle of the hump, it's symmetrical to the left and the right side of it, right? Which means that between one end of the curve and the first solution, that gap is 120. That's the same gap between the second solution and the other end of the curve at 360, right? Which means to get the next solution here, we take away 120 from 360. If we do then 360 take away 120, we get 240. And that would be the next solution there. Okay, those are the only two solutions we can see then between 360 and 0. There we are then. So those are my two solutions here. Therefore then, if we just combine these, we can combine these two different solutions together. So overall, theta would be 0, 360. 120 and 240. There we are. Okay, cool. Okay, part B. We need to solve sine squared theta minus 30 is a half. And again, that's between 0 and 360. Okay, cool. Now, if we have a sine squared, right? So then, remember, like we're solving the equation, say x squared is 1, we'd have to square root both sides, right? So then sine theta, well, we wouldn't have theta, we'd have sine of theta minus 30, would be plus or minus the root of a half. If we put that root half in the calculator, we get root 2 over 2. Okay, that's what it simplifies down to. Okay, so then again that means we get two different equations then. So either sine of theta minus 30 is root 2 over 2, or sine theta minus 30 is minus root 2 over 2. So again, we need to solve these two equations separately. Okay. Right. Okay. So if I label that equation 1, equation 2, so then we solve them separately. So let's do with this one first. Now, we have the angle's a bit different at input, right? It's not theta, it's theta minus 30. Our interval is for theta, not for theta minus 30. So we need to adjust for that then, don't we? So if we want theta minus 30, we need to subtract 30 to both sides, right? So 0 minus 30 would be minus 30. And 360 minus 30 would be 330, okay? And that is my interval I need to be working in then, right? That's the values I need to consider. So let's solve then, right? So firstly, let's work with this one. If we do firstly inverse sine of root 2 over 2, we would get 45 degrees, okay? That means our angle, theta minus 30, could be 45. Then to get the next solution, we can consider the sine graph. Okay. So again, we have, say, 360. So our first solution was 45. 45, there we are. So the next solution will be that way along there. So again, because in the middle of the hump, it's symmetrical either side of the hump, that means that the gap then between one end of the curve at 0 and the first solution would be 45. That's the same gap between the second solution and the other end of the curve at 180. That'd still be 45 as well. Okay. Right. So then to get the next solution then, we'd have to take away 45 from 180 to get the next solution there. So 180 take away 45 would be 135. Cool. Okay, so those are the two solutions then, between 360, but we need to also consider the negative angles as well, because it's not 0 at the end, it's minus 30 there, right? So we can go backwards by subtracting 360. So remember, once we found the first two solutions, we can add or take away 360s, because that's when the graph repeats, right, to get other solutions. So if we subtract 360 from 135, we would get negative 225. Well, actually, that is below minus 30, so we don't need to consider that. If we subtracted 360 from 45, we would get minus 315. So again, that would be below minus 30. And so obviously that's all our values then, between minus 30 and positive 330, right? So actually there we are. Okay. So if I recap then, we have theta minus 30 could either be 45 or 135 degrees, right? So then we want to solve for theta, right? But we have theta minus 30. So then to get theta, we need to add 30 to both sides. So then theta, if we add 30 to all our values here, 45 add 30 would be 75. And 135 add 30 would be 165. Okay. And those are my two values for theta. Cool. Right, okay. So if I get rid of that then, we then need to solve this equation up here. This second one, sine of theta minus 30 is minus root 2 over 2. So again, let's do inverse sine of minus root 2 over 2. We would get minus 45. Okay, so then theta minus 30 could be minus 45. So then to find the other solution, then the next solution, if we consider the sine graph, the 360 be there. Well, minus 45, we would have to go backwards a little bit then, wouldn't we? There we are. So that'd be minus 90. So minus 45 would be there, right? So then the next solution would be there, right? The next solution after minus 45. Well, to obtain that solution then here, well, again, recognise the gap between minus 45 and 0 at the origin. That is 45, obviously, of course. That is the same gap between when it's at 0 at 180 and the second solution there, right? That gap would also be 45. Again, the symmetry of the graph, because again, it's symmetrical in the middle of the hump. So again, the left side is the same as the right side. So there we are. Okay. Now, so then to get the second solution then, we have to add 45 to 180. So if we do 180 add 45, we would get 225, right? So the next solution would be 225. Right, so then to get the other solutions after that then, we can just add or take away 360. But obviously if we take away 360 from 225, we would get minus 135. But we don't want that because that's below minus 30. So we don't want that one. And so then obviously we we shouldn't subtract 360, we shouldn't go backwards, or else obviously we get more negative values. So those are all the values less than minus 30. So then let's add 360 then to my values here. So then minus 45 add 360 would be 315. And then hopefully you spot, if I added then 360 to my next value, 225, that would be above 330 there, okay? Because 225 add 360 would be 585. 585, that'd be greater than 330. So that'd be outside the range. So we shouldn't have 585, okay? That'd be the next number. We shouldn't have that. So those are my values then, really. And actually, we can't have minus 45 either. Obviously, that's the first value we got. We used that to work out the other values. But minus 45 is actually less than minus 30. So we have to reject that solution too. So actually, the only two solutions we get is 225 and 315. Okay? Right. Therefore, then, if we summarise, my two values for theta minus 30, it'd be 225 or 315. But of course, I want to solve for theta, so I need to get rid of the minus 30, so I add 30 to both sides. Therefore, theta then would be, if I add 30 to my values, 225 add 30 would be 255 degrees, or 315 add 30 would be 345. And those are my two solutions here. But of course, we solved both equations. So overall, we need to combine them to get a final list of solutions. If we combine these two lists, right, that are boxed, therefore theta then would be 75, 165, 255, or 345. And there we are. That's my final set of solutions for theta. Cool. There we are. Okay, so we've got this question then. Find the values of x in the interval of minus 180 to positive 180, satisfying the equation. I should note, this is from the textbook. This is wrong here, so I need to add a correction. It's not 9 sine squared, it's sine of x, okay? So we had the equation 2 cos squared x plus 9 sine of x, not sine squared. But sine of x equals 3 sine squared x, okay? Correction there, the textbook writes the question wrong. I did check the working and the textbook answer. That's the correction there, okay? Textbook, right? But there we are, okay? So this is the equation we need to solve. Now, hopefully you resemble, we sort of have a quadratic for sine x, because we have a sine squared and a sine. But we also have this cos squared. Now, with these sort of equations, the whole idea is if we have a quadratic term, right, of a trig function, we only want one of the trig functions, right? So we don't want any causes, right? We just want sines, essentially. So we kind of want to get rid of the cos squared, but hopefully this cos squared and the sine squared as well, but the cos squared is resembling the identity cos squared x and sine squared x is 1. Well, actually then, if I want just sines, if I just want sine and not cos, I can rearrange this, can't I? So then cos squared would be 1 minus sine squared, okay? Then I can substitute that in to here, right, for cos. So therefore then we get that this is 2 lots of 1 minus sine squared x plus 9 sine x. And then I'm going to move this 3 sine squared to the other side, equal to 0. And now hopefully you start to see we're resembling a sort of quadratic equation for sine, right? There's a bunch of sines, right? Sine squared, a sine, and stuff like that, right? Equal to 0. So we're starting to get an equation now, okay? There we are. So then we're going to expand this. So we get 2 minus 2 sine squared x. Then we have plus 9 sine x minus 3 sine squared x equals 0. Then I can just collect the like terms. So I have minus 2 sine squared and minus 3. That'd be minus 5 sine squared x plus 9 sine x plus 2 equals 0. Now hopefully you recognise that is a quadratic, right? It's a disguised quadratic. Because it resembles a quadratic, but it's not exactly one. So to make that clear, we can use a substitution, because then we can say that u is sine of x, right? So then if we put that into our equation, this becomes sine squared would be u squared, right? So that would be minus 5u squared plus 9 sine x would be plus 9u plus 2 equals 0. And then we can now that is a quadratic, right? Very explicitly. Okay, so we can solve that via the formula, let's say. So if we solve that, we're going to get u is minus 9 plus or minus the square root of 9 squared minus 4 lots of minus 5, 2 over 2 lots of minus 5. And then if we put that in the calculator, we get u is 2 or u is minus a fifth. Okay. But of course, originally we have sine x, not u. So we can use this sort of substitution we made to convert back into sine x. So if u is 2, that means that therefore sine x is 2. Or sine x is minus a fifth. Okay. By the way, if you are comfortable, you don't have to do this u stuff. I'm just making it very explicit, right? That this is the underlying quadratic, right? If by making this u substitution, right? If you're very comfortable, you can just skip that out and just solve it straight away. This sine squared equation to get sine x is 2 or minus a fifth. But I'm doing it step by step, right? But there we are. Now, so that means we either have the equation sine x is 2 or sine x is a minus a fifth, and we need to solve both of them. Remember, we're in the interval minus 180 to positive 180. There we are. So first of all, this equation here, so sine x is 2. If we were to then do inverse sine of 2, we would get, and I know what will happen, but we would get something, a math error, right? The calculator gives me math error, okay? Obviously, that's what happens. So we can't solve it then, but why? So there are going to be no solutions then if we get a math error to this. So I'm going to say it's undefined. So no solutions, okay? No solutions here. But why? Because the sine graph, if you look at the sine graph, it really, the maximum it could be is 1, right? That means if we have 2, sine x equal to 2, well 2 would be up here. It would never ever meet the curve, right? So 1 is the maximum. If you go above 1, the sine curve won't be solvable, right? So this equation will have no solutions because of the proper reason being that sine x has a maximum of 1, okay? Oh. Therefore, sine x cannot be 2, okay? So if it can't be 2, there are no solutions to this. So that's a technical reason, but obviously if you were to just, you know, follow the process, you do inverse sine of 2, you would also get, the calculator would like say math error, right? It wouldn't work, right? So it'd be undefined, and it's undefined because again, the sine graph has a maximum of 1. It can't go above 1, so it can't be 2, okay? So there are no solutions here, so we can't solve it, okay? But this is the proper technical reason, right? Because of the graph, right, tells you the maximum of 1. Anyway, so let's move on to this. We can solve this in this case. If we do inverse sine of minus a fifth, we would get minus 11.536 blah 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 degrees. Okay, so my first solution would be x is minus 11.536 blah blah blah. So to find the other solutions then, let's consider the sine graph again. Uh, 360. Well, we have a negative 11, the negative angle, so let's go a bit backwards then to minus 90. There we are. So minus 11 would be about there really, wouldn't it? So if we read off the graph, the next solution would be there. Right, so minus 11 would be there, squeezing it in. So then this next solution here for x then, well again the symmetry in the middle of the hump is the same, which means eventually, basically, the gap between minus 11 and when it reaches 0, that gap would be 11, right? That is the same gap then between between 180. I'm gonna have to squeeze it in here. 180 and the next solution x, right? That same gap then between 180 and the second solution, the next solution would also be 11, right? Which means we need to add on this 11, well technically the 11.536 from our calculator, add that to 180 to get the second solution there. So if we do that then, 180 add 11.536, that would get me 191.536 blah 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 degrees. So that'd be my next solution, right? Okay, but of course we are actually we can only go up to 180, right? This exceeds 180, so that we actually can't have that solution. So we do not add 360. What about if we go, obviously we have to go to minus 180. Let's see what happens by taking away 360, right? If we take away 360 then, let's go back. If we take away 360 to this first solution, 191, we would get minus 168.463. So that's taking away 360 from my solution there to get this solution, minus 168. So whilst we can't have that one, if we subtracted minus 360, we get this solution here, which is above minus 180. So we can have that one, right? Now, if we subtracted 360 to the next solution, minus 11, well, that would be below minus 180, right? So we do not subtract any more 360s from my other solutions. So therefore, these are my two solutions there. Okay. So by the way, when you have a negative, always check by subtracting 360 your values. You might be missing a negative solution there, right? So be very careful. If you're going backwards, you do need to subtract 360, depending if the interval has a negative, right, in this case. So do be careful. So even though we have to subtract, we can't accept this solution 191, we still need it because we then need to subtract 360 to it, which got us this other solution here, which was valid. So do be careful, okay? There we are. So those are my two solutions then. So therefore x could be minus 11.5, I'm going to round it to one decimal place, or minus 168.5 to 1 dp. And there we are. Those are my two solutions then. And obviously, again, as a reminder, there are no solutions here. So overall, my solutions are just these two there. Okay. There we are. Okay. Right. Let's have a look at this exercise then, and we're going to explore this sort of idea of equations maybe not being solvable in this question here. So let's have a look at this. Part A, we need to show that the equation cos squared x is 2 minus sine x can be written as sine squared x minus sine x plus 1 equals 0. So again, hopefully you notice this equation we need to get to has just sine x, but we have a cos x. but this is cos squared. So hopefully that's ringing the alarm bells again. We need the identity sine squared and cos squared is 1. Well, I can get cos to sine by rearranging. So then cos squared would be 1 minus sine squared. And then I can sort of substitute that in then into here, right? So then I can say that therefore 1 minus sine squared x instead would be 2 minus sine x. And then we can rearrange, right? So if I move the left side to the other side, if I add sine squared first, I'm going to get sine squared x. Plus 2 minus 1 would be plus 1 minus sine x. And then if I just rearrange it ever so slightly, I get therefore sine squared x minus sine x plus 1 equals 0. Okay, equals 0 there. Okay, there we are. Cool. That's for 2 marks. So again, hopefully you start to notice the sort of common strategy now, where we're going to often, to get a quadratic equation or some sort of square term for sine or cos, we're going to need to eliminate by using that sort of identity, right? So any time you see a cos squared or sine squared, you should be considering maybe this identity there, okay? There we are. So that's part A. Part B then says, hence show that that same equation, right, cos squared is 2 minus sine x, has no solutions. So it's very similar to what we talked about last time, right? Now, obviously, let's go how we would normally do it, right? So how would you go, if you, obviously, we'd need to solve this, right? That equation is equivalent to this one. If we were to solve it, then we'd use the formula. Well, obviously we would have to obviously this is a disguised quadratic, so we can say that u is sine x. Then we would get sine squared would be u squared minus sine x would be minus u plus 1 equals 0. Then we would solve by the formula. So u would be plus 1 plus or minus square root of minus 1 squared minus 4 lots of 1, 1 over 2 lots of 1. And so if I put that in the calculator, I imagine it would not be very nice because it says there's no solutions, right? Let's have a look. Right, what I get here, if I copy what the calculator says, I get 1 plus root 3 and then this weird letter I over 2. Now when you see this I, or if it looks a bit weird, it basically means it's not solvable, right? When you look at, if you look at further maths or further maths in general, you will look at something called complex solutions, but I'm not going to do that here. All you need to know is that actually this has no solutions. Then if the calculator gives a weird letter, it has no solutions, right? And that's because of the fact as well that the square root, if you look, the square root's going to be negative. If we were to simplify it, then I'd have 1 plus or minus the root of minus 1 squared be 1, take away 4 times 1 times 1, that'd be take away 4. Well, that'd be root minus 3 all over 2. But that's a negative then, so it's undefined. Or yes, so u is undefined, so no solutions here, and that's it. Okay, and there we are. Now, this is a bit, I find it a bit of a rough way of doing it. What's the more formal, proper way of doing it? Remember when we looked at discriminant, if it's talking about no solutions, the discriminant of a quadratic, remember the discriminant is b squared minus 4ac, the discriminant has to be less than 0, which again means the square root has to be negative in this case. So let's compute the discriminant of this then, right? Of our quadratic. B squared minus 4ac would be minus 1 all squared. Take away 4 lots of 1 lots of 1. That would get me minus 3, which is less than 0. Okay, so therefore there are no real solutions here. Okay, so therefore we can't solve the equation, right? So we can't solve this quadratic, so we can't solve this trig equation we got up here, right? And so there we are. So therefore, there are no solutions because the discriminant of the quadratic is negative, okay? So yeah, so do remember, you can prove there are no solutions to a quadratic by considering the discriminant, even if the it's not a proper quadratic. You know, we have sine squared, right? This was just a disguised quadratic, this sine squared sine on 1, but you can convert it into a proper quadratic, which then we can use a discriminant on, and then we showed there are no solutions to it. So there we are. So yeah. Okay. Okay, so we got this question here, and here we're asked to find all the solutions in the interval between 0 and 180 for 2 sine squared of 2x minus cos of 2x minus 1 equals 0. Okay, between 0 and x and 180. Cool. So again, the same sort of situation. We have sort of squared term and a normal term and then a minus 1, right, a number. It kind of resembles a quadratic then, right? But again, I have sine and cos. I kind of want them both, you know. I only want one of the trig functions. I don't want sine and cos, just one of them. But again, this sine squared hints at the identity sine squared sine squared theta and cos squared theta is 1. If I rearrange that, then I can get sine squared is 1 minus cos squared. And so therefore then, if I put that sine squared in there then, substitute it here, I'd get 2 lots of 1 minus cos squared. Now for theta, our angle is 2x, okay? So there we are. Minus cos of 2x minus 1 equals 0. So then I need to expand this out. So I'm going to get 2 minus 2 cos squared of 2x minus cos of 2x minus 1 equals 0. And so then I can sort of simplify this a bit more. So I'm going to get minus 2 cos squared of 2x minus cos x, cos of 2x. And then 2 minus 1 would be plus 1 equals 0. Okay, so now hopefully you see that is a quadratic for cos in terms of cos. So then I can, again, to make it very clear it's a quadratic, I can say that u is going to be cos of 2x then. If I do that, then I'm going to get, well, cos squared of 2x would be u squared, so that'd be minus 2u squared minus u plus 1 equals 0. Then I can solve that, right? So then I'm going to get u is 1 plus the minus square root of minus 1 squared minus 4 lots of minus 2 lots of 1 over 2 lots of minus 2. And therefore u, if I solve that then, put that in the calculator, I get u is a half, or u is minus 1. Okay, so those are my two solutions, but I don't want u, I want cos, so I can bring that back in then here. Therefore either cos 2x is equal to a half, or cos of 2x is equal to a negative 1. Okay, so those are my two equations, and again we need to solve them separately then. So also bear in mind then, before we solve our interval, as a reminder, was here 0 to 180. So it's going to be 0 to 180, but our input, right, our x, our angle is not just x, it's 2x. So I have x here, so then to account for 2x I need to double it, right? So then I'm going to get 0 to 2x, and then 180 times 2 will be 360. That is my interval I need to be working in. There we are. So then we just, okay, then let's just solve as normal. So let's solve this. So firstly, we do inverse cos of a half. That would get me 60. Cool. So then that means 2x, our angle, right, 2x then could be 60. But the other solutions then, we can consider the cos graph to help us work that out. There we are, something vaguely like that. So 360 there at the end there. So 60 would be, say, there. So again, because it's symmetrical in the middle, right, of the hump, right, the graph's symmetrical in that way, we at either end then of the curve and the first solution, that gap is 60. It's the same sort of distance. If we read off the graph then, that's my next solution. So if I read off the graph then, that's the same gap between the second solution and the other end of the curve at 360. That gap is 60. To work out the next solution then, I need to take away 60 from 360. If I do that, I get 300 as my next solution. Okay, so 300 there. So those are my first two solutions. And actually those are the only solutions then between 0 and 360. Right? So there we are. So those are my two solutions then. 2x is this. So, okay. So 2x is 60 or 300. Therefore then, I need x, right? So not 2x, but x. So I'm going to divide everything by 2. So then x is going to be 60 over 2 would be 30. And 300 over 2 would be 150. Okay, and those are my two solutions there. Cool. Okay, now we're going to solve this equation then. So cos of 2x is minus 1. So again, let's do inverse cos to get me 180. So again, if I can, that my first solution for the angle 2x then is going to be 180. To spot the next solution then, let's consider the cos graph. Well, 180 is going to be there. Well, actually, if you read off the graph, between 0 and 360, so 360 there, that's my only solution between 0 and 360, right? 180 is the only solution there, really. So that really is the only solution then, actually, 180, right? Okay. So then if 2x is 180, my other solution, so then to get x then from 2x, I need to divide by 2. So then x is going to be 180 over 2, which would be 90. And that is my solution there, okay? Okay. And again, by the way, there's only one solution here, but if I was to find more solutions, if I needed, say the interval was a bit different, I could just add or take away 360 in the same way with the other solutions on the other examples, right? Just because there's only one solution here, there, don't freak out. Obviously, if we were to continue the graph on, the next solution after that would be 360 away from that, so it repeats, okay? Anyway, so there's only 180 there, so my overall solution is 90, okay? Okay, so then we can combine them then. So therefore, my solution is x is 30, 150, and 90, okay? Doesn't matter what order you do it in, obviously, it's not ascending order, but anyway, those are my final answers there. Cool. Right. Let's have a look at this question then. It's a challenge question, but I don't think it's the worst question in the world. So let's have a look at it. So we need to solve the equation tan to the 4 x minus 3 tan squared x plus 2 equals 0 between 0 and 360. Okay. Now, again, this hopefully resembles a quadratic, but it's a bit weird. It's not just tan squared and tan. We have tan squared and tan to the 4. Well, again, if I then said that u is tan x, right? Then we would get the quadratic u to the 4 minus 3u squared plus 2 equals 0. Hopefully you see that, right? If u is tan x, then tan to the 4 is just u to the 4, right? And so on for squared. Anyway, that's my quadratic for u, right? But obviously it's not a quadratic. because I have a u squared and a u to the 4. I like my quadratics looking like ax squared plus bx plus c. That's what I can work with. But I have u to the 4, u squared. But again, this is another disguised quadratic. We've got a disguised quadratic in a disguised quadratic, right? So we've got disguised quadratic with the tan, but then we have disguised quadratic with the u to the 4, right? So we need to do another sort of simplification, right, if you will. Now, hopefully, what if I said instead, Dan, instead then, that u is tan squared x, right? If I said u is tan squared x instead, then this equation would become, well, tan to the 4 would be tan squared squared, right? So if u is tan squared, then u squared would be tan to the 4x, right? Hopefully you can see that. So then it become u squared minus 3 tan squared would be minus 3u. And then plus 2 equals 0. Now that is an actual proper quadratic then, right? So there we are. So hopefully you see that's probably the hardest bit about, probably why it's a challenge question. This is probably the hardest bit. Hopefully you're convinced that that is the quadratic we end up with, right? Hopefully you can see how we got to this quadratic. Anyway, so we can solve this now in the usual way. So then u would be, say, by the formula, 3 plus or minus the square root of minus 3 all squared minus 4 lots of 1 lots of 2 over 2 lots of 1, which would get me either u is 2 or u is 1. Okay, so therefore then I don't want u, but I want this tan, right? So I said up here that u is tan squared x. So that means either tan squared x is 2 or tan squared x is 1. And actually, again, what makes this a bit trickier, or I guess a bit more work, I should say, well, we have tan squared. This is an equation in itself. So I'm going to need to do square root, right, of this side. So if tan squared is 2, then therefore tan x would be equal to plus or minus a root 2, right? Or tan x, then if we have tan squared is 1, then tan x will be plus or minus root 1. Well, root 1's just 1, so it's plus or minus 1. So therefore then we've got 4 different equations to solve then. So either tan x is root 2, positive root 2, tan x is minus root 2, tan x is positive 1, or tan x is negative 1. We need to solve all 4 of them in the range, again, between 0 and 360. Was it? Yes. Okay, there we are. So we just need to solve them. Fairly normal equations, but we need to solve all 4 of them. Okay, so firstly, tan x is root 2. If we do inverse tan, we get 54.73 blah 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 degrees. Right, so if I then then the first solution would be x is 54.73 blah blah blah. So then if we can find the other ones, let's sketch the tan graph to help us see. So a tan graph looks like this. So 90 as the asymptote there, then 270 there, and then it goes back 360 there. So 54 degrees will be about there, right? 54.7 there. If we read off our graph, the next point would be there. But that's going to be 180 long. That's the graph repeating itself, 180 more, right? Hopefully you can see that. Think back to when we looked at the tan graph. That's 180 extra, right? So then we just need to add 180 on to this next solution here. So 54.73 add 180, then gets me the next solution, 234.7 35, blah, blah, blah. If we add another 180 on, we get 414.735. But we're only between 0 and 360, right? That is over 360, that 414. We have to reject that. So those are my only two solutions then, right? So therefore, to say to one decimal place, x is either 54.7 or 234.7 degrees, okay? There we are, to one decimal place. There we are. Right, so then we solve this second equation in the same way. So inverse tan of minus root 2 would get me minus 54.73. So then my first solution would be minus 54.73. So then to get the next solution, let's consider the tan graph. Oh, it's a bit slanted, isn't it? Let's try and draw that again. So 90 will be there. 270. Then 360 there. Well, minus 54, we'd have to go back a bit, wouldn't we? There we are. So minus 90 would be there, right? The asymptote there. So minus 54 would be about there, right? Minus 54 there. So that's the first point. The next solution would be there. Again, hopefully you can spot that's 180 long, right? Obviously the graph isn't the best drawn. I do apologise. I'm trying to squish it in because I need to make a lot of room here. But the next solution is 180 long. That's the whole idea of the tan graph. Hopefully you picked up that with tan, the solutions are just 180 each time, right? It's quite simple, the tan graph. So if I add 180 onto this solution here, I get 125.264, blah, blah, blah. If I add 180 onto this one, to get the next solution, I get 305.264 degrees. And hopefully you spot then, if I add another 180 onto 305, I'd be going over 360. So I need to stop it there. That's my full list of solutions. So overall then, from here, x is either minus, well, this would be rejected as well, right? Minus 54 is negative. It also has to be above 0, right? So no negative numbers either, right? So our two solutions is either 125, right here, 125.3, or 305.3, right, to one decimal place. There we are. Right, so then this next solution, I need to make some room, if it lets me. Okay, I'm going to try and space this out a little bit, actually. So we needed to solve next, tan x is 1, and over here, tan x is minus 1. So if we were to solve tan x is 1 then, my inverse tan of 1 would get me 45. So then my first solution is 45. But hopefully from now, if you look at the tan graphs you looked at before, it's just repeating every 180 all the solutions, right? So 45 then, the next solution after that, by adding 180, would be 225. If we added another 180 on, we'd get 405. But actually, that is above 360. That is outside our range. So we need to reject that one. So overall then, x is 45 or 225 in this interval here, between 0 and 360. There we are. And lastly, tan x is minus 1. If I did inverse tan of minus 1, I get minus 45. Need a bit more room. There we are. So tan inverse of minus 1 is minus 45. So then my first solution would be minus 45. So then again, with tan, it's just adding 180 on, right? Hopefully spiked that with the first two solutions. So adding 45 on, or 180 on, sorry. We get 135 as the next solution. If we added another 180 on after that, we get 315. And then if you notice, adding another 180 on would be above 360. So any more solutions after that will be outside the range. But also this minus 45 is negative. That's also outside the range because it's less than 0. So we reject that then. So overall my two solutions are 135 and 315. And there we are. So we solved all four equations, so just combine them together. So overall, my final list of solutions is going to be 54.7, 234.7, 125.3, 105.3, 45, 225, 135, and 315. And that's all to one decimal place, right? So that is my final. Right, it's so long I can't even do it all on one screen. So those are my final list of solutions. Okay, there's a lot of them. Okay, we got there. So hopefully that made sense. But yeah, like I said, the trickiest part of this question, I reckon, is to get to the get to the equations, right? Not maybe solving them, but actually arriving at this quadratic, right? So being able to recognise that this, if we said u is tan squared of x, we get to this quadratic here, okay? Which we then can solve, okay? And then we went from there. Okay. Now let's have a look at an exam question then. Exam question to finish off. Right, so we firstly need to show that the equation for tan x equals 5 cos x can be written as 5 sine squared x plus 4 sine x is minus 5 equals 0. Now what's interesting is that both tan and cos have both disappeared and there's only sine. Now that's interesting. Okay, so how are we going to do that? So tan and cos need to go away and they need to be just sine. Well, firstly, tan, I can get that in terms of cos and sine, right? I can say that tan, remember our identity, that tan x is sine over cos, right? Well, we can bring that in then. So we can say 4 lots of sine x over cos x is 5 cos x. Right. So then we can say that 4 sine x over cos x, if we just expand the bracket, is 5 cos x. Okay. And then I can sort of times across, right? I can times the fraction, right? Get rid of the fraction by timesing both sides by cos x. So then 4 sine x would be 5 cos x times cos x would be cos squared x, right? Now that starts to look a lot more familiar to the examples we just did, right? So then cos x, remember my final answer is just it's just in terms of sine, right? Up here. But cos squared, so remember cos squared x add sine squared is 1. I can rearrange that cos squared, can't I? Then cos squared I can say is going to be 1 minus sine squared, right? And then I can bring that in as well. So then cos squared is 1 minus sine squared. I can bring that here. So therefore 4 sine x is 5 lots of 1 minus sine squared x If I then expand this, I get 4 sine x equals 5 minus 5 sine squared x. If I then bring the right side to the this side, the right side to the other side, if I add 5 sine squared here, sorry, if I add the 5 sine squared, right, to both sides, I get 5 sine squared x. Add 4 sine x, and then if I subtract the 5 to both sides, minus 5 equals 0. Hopefully that should be what they wanted. 5 sine squared, add 4 sine x minus 5 equals 0. Great. Cool. Right, part B then says, hence solve between 0 and 360. The same equation, right? 4 tan x is 5 cos x in one decimal place. So again, a very, very common exam situation. In the first part, you needed to prove something or, you know, get a simplifying equation, right? And then you need in part B to solve it, right? And we can use our alternative equation. We can bring that in, right? So this original equation, 4 tan x is 5 cos x, right? Up here, remember that's equivalent to this equation we worked out. So we can just solve that one instead, right? So then we can solve effectively 5 sine squared x, add 4 sine x, minus 5 equals 0, right? And that we know how to solve, right? So between 0 and 360. Now they're a bit weird with this one. So it cannot be 0, but they said it could be 360 because it's greater than or equal to. A bit weird, sometimes a bit weird in exams. But that's the interval you need to work with. Remember, always pay attention to the details. So we need to solve this then. And again, that should be a fairly sort of common sort of question that I know how to solve from looking at the examples I just did. So this is again a hidden quadratic, right? A quadratic, a sine square term, right? And a sine x and so on. So I can say that u, again, to make it clear to what quadratic I'm going to get, u is going to be sine x. So then I'm going to get 5u squared plus 4u minus 5 equals 0. Then I can solve that quadratic, right? Which I know how to solve. So then u is going to be minus 4 plus or minus the square root of 4 squared minus 4 lots of 5 lots of minus 5 over 2 lots of 5. And that's going to be u equals, if I put that in the calculator, okay, u is minus 2 plus or minus root 29 over 5, okay? So, okay, not the nicest number. So, that means then, how should I go about this? I'll make a note here that then u, as in decimal form, right? Remember, if you've got a nasty fraction like this, it might help to, for yourself, to sort of convert this as a decimal. So u is 0.677. That's the positive case. Or it's negative 1.477. Okay, so hopefully that visualizes what's going on here. Nasty fraction, but these are the two actual values. That's what it means. So again then, so u is going to be minus 2 plus root 29 over 5, or the negative case, right? U is negative 2 negative root 29 over 5. Again, the positive fraction here is 0.67. The negative is just minus 1.47, okay? But yeah, there we are. But again, we don't want u, we want sine x. So we need to bring that in. So that means therefore that sine x is a minus 2 plus root 29 over 5. Or sine x is minus 2 minus root 29 over 5. And so therefore we've got two equations then, right? So this will be equation 1 and this will be equation 2. Okay, so we can proceed with solving the first equation. So if I do inverse sine, now by the way, obviously some people may be like, oh, why don't we just bring the decimal in? I did that to help. there could be an issue with rounding errors if you round a bit too early in the question. So yeah, so I'll probably just stick with the full sort of proper fraction, the exact form, right? But yeah, maybe it won't matter. I don't know. But there we are. Okay, so sine x is going to be this. So then if we do inverse sine of this whole thing, we get okay, 42.612. There's no avoiding the decimal here. Obviously, the calculator just gives you that number. So that's going to be my first solution then. X is 42.612. So then to get the next solution, let's consider the sine graph, right? There we are. So 360 there. So 42 is going to be, say not there, right? 42.6. The next solution is there for x. Again, then to get that second solution, the symmetry of the graph, right? So at one end of the curve, and the first solution is going to be 42.6. That's going to be the same gap between the other end of the curve at 180 and the next solution, which is 42.6. Therefore, to get the next solution, I need to subtract this 42.6, right, from 880. So 180 take away this 42.612 gets me the next solution of 137.387. So if I add that here, there we are. Okay. Okay, let's look at our interval then. So those are my first two solutions. To get the other ones, I need to add or take away 360, right? Do I need to do that? Actually, no, I don't, because I'm only between 0 and 360. So those are my only two solutions then, without adding 360 on, okay? Therefore, overall then, x is 42.6, or x is 137.4 to one decimal place. What did it say to round to? One decimal place, was it? Yes, one decimal place. Okay, so we're good there. Okay. Okay, so those are my solutions here. Cool. Now, we need to then solve sine x here is minus 2 minus root 29 over 5. If I were to inverse sine that, hopefully you spotted what's going to happen, particularly when we looked at the decimal form of the answer up here, right? Where was it? Up here. This fraction is equivalent to minus 1.47. Hopefully you can spot what the issue is going to be here. But if I did inverse sine, well, if I do that in a calculator, I get a math error, okay? So it's undefined. But why is it undefined? So we can't solve it then, but why is it undefined? Well, this minus 1.47, that's bigger than minus 1. Well, look, less than minus 1, right? If we were to consider the sine graph, right? Remember, last time we talked about when we ran into this problem, right? Its maximum was 1. So then when we said it was 2, there were no solutions, right? Because it can't be above 1. But also the minimum, right? The lowest it can be is also minus 1, right? Down there. That means it can't be below minus 1. Well, minus 1.47 is below that, right? So it'd be, say, like down there, right? Minus 1.47. That would never meet the curve, right? Because it's below the minimum, right? So, what we can then therefore will say is that is undefined as minus 2 minus root 29 over 5 is less than 1, okay? So there are no solutions here. And I should say that therefore that's because sine x cannot be equal to minus 2 minus root 29 over 5. Okay, so it can't be equal to this value because it's outside like the range that that sign can be. Sine has to be above minus 1, sorry here. Can't be less than minus 1. So sine has to be above minus 1, okay? So anything less than minus 1, that cannot happen. So therefore there are no solutions. But actually overall then, my solutions are exactly just 42.6 and 137.4, right? And there we are. So final part of this question then. Part C says, hence find the number of solutions, okay, to the equation 4 tan of 3x is equal to 5 cos 3x in the interval 0 to 1,800, okay? Given a reason for your answer. Okay, so they do like to ask these from time to time about number of solutions to a more complicated equation. Now, okay, so we'll do part C here then. Let's have a note here. Part C. We had the equation then for, what was it? 4 tan 3x is 5 cos 3x. In the interval 0 to x to 1,800. Was that it? Yes, obviously it could be equal to. Anyway, yes, that was the question. Right, so again, that's hopefully you recognise that's the same equation as sort of what we got, you know, in part A, right? It's sort of very similar, right? In part A, we had 4 tan x is 5 cos x. Now we have 4 tan 3x is 5 cos 3x. So all we need to do is just replace the angle, right? Instead of x, we now have 3x. But then everything else to do with solving the equation in part B would be the same. The only difference is we need to adjust for the fact we have 3x, not just x, right? So actually, we can just use our equations in part B, but then just replace x with 3x, right? So remember we ended up solving sine of x is equal to this, and then sine of x was negative. But obviously the second equation here had no solutions. And actually with this, sine x is minus 2 plus root 29 over 5. We got these two solutions here. So if I were to recap then, basically we need to solve then, instead of sine x is minus 2 plus root 29 over 5, we would get to solving sine of 3x. So from part B, solve sine of 3x is equal to this minus 9, what was it, minus, what's the fraction, minus 2 plus root 29 over 5, right? Now we don't need to go on solving that because it already said the number of solutions, right? Okay, but the key with this then is to consider, with these sort of questions, is to consider how many solutions are in the first 360 degrees. Well, in between 0 and 360 degrees, right? 0 and 360 degrees in part B, that this equation, right? Remember here that are boxed. There was only two solutions, right? So there are two solutions to sine x in 360 degrees, right? But again, remember, we have sine 3x. We need to adjust our interval, right? As always with solving. So therefore, if x is between 0 and 1,800, that means 0 has to be between 3x. And then we times this by 3, we would get 5,400, right? So that is our new interval we need to work with, right? So those are the range of values we need to go up to. So that's the angle, that's the degrees we need to go up to. Now, 360 degrees then, right, essentially means two solutions, right? We saw in part B, this equation has two solutions in 360 degrees, right? Well, then that means then we need to go up to 5,400. So let's see what 5,400 divided by 360 is. How many times do we need to repeat 360? So 360 is two solutions. What I'm basically saying is how many times do we need to repeat that 360 to get to this end point there. But then we just do 5,400 over 360. That actually is 15. So that's quite nice. So therefore then, if you times by 15 to both sides, that means that 5,400 degrees is 30 solutions, right? And there we are. So therefore, total of 30 solutions to that equation. Okay, cool. And there we are. So that's that then. So that's hopefully that's the end of the chapter. Hopefully you feel confident now to solve various trig equations that we looked at in the first three chapters, and you're comfortable with applying the trig identities as well. So the cos squared sine squared is 1 and tan is sine over cos. You do need to remember them again, but hopefully with enough exposure you start to just pick it up anyway, right? But that's the end of this chapter, so I'll see you next time.